So it's Alessandro Tavoni of the London School of Economics. Alessandro got his PhD in economics here in the School of Environmental Economics all'Università di Venezia in Ca' Foscari. Sorry, thank you so much. And but in the meanwhile, spent time by Simon, so he's very well exposed to the ecology thing. Now he's a professor at London School of Economics. So Alessandro, the floor is yours.
Thank you, Andrea, for having me. It's a privilege for me to be here in such a honor place, and it's also very tricky to speak after all these very eloquent and smart professors. So I will try to make it interesting and hopefully not repeat. I mean, we have touched on many of these issues in the morning, and I will come back to public goods ideas and also threshold effects. So this will also resonate with Matteo's lecture as well. Let me just give you briefly the outline of what I will be presenting. So first I will talk about some evidence that we have gathered in the lab. And when an economist speaks about the lab, it means playing around with students. So this will become more apparent in a second. And finally, I will have a bit of theoretical work on common pool resources, work that I've been doing with Simon when visiting him during the PhD in Princeton and also more recently. And then I will try to extrapolate. Let me start by, we have touched also on this issue of cross-disciplinarity and the need for more interaction among different scientists, even in conversations with some of you during the breaks. And as a motivation for my effort in reaching out to ecology and other disciplines, I thought I would put up a couple of slides. Also because being an economist, I tend to have very boring slides. So I thought some colorful and pretty pictures with networks would help keeping you engaged in the afternoon. It's very warm and we're getting tired. The point of this hierarchical map of science is to show traffic among disciplines. You can probably not read very well all the different fields, but they're grouped into main fields. So you have the life sciences, social sciences, and physical sciences, as well as ecology and earth sciences. And what is apparent, I think, so if you look at social sciences over there, let's see, I can point. So here we have social sciences, economics is pictured here in the middle. These graphs here shows you the traffic between different macro areas. So you see that there's quite a bit of insularity, especially with respect to the social sciences and economics. There isn't much reaching out across the field. And if we look at citation patterns, this is probably even harder to read. So again, economics is right here. You see that contrary to the natural sciences, there is quite a bit of inbreeding going on. And this, I argue, is a problem for studying environmental problems and coupled social-ecological systems. I will come back to this. This is the same slide, but focusing on the trajectories from economics to the others. And as you see, again, this citation flow is quite clear in showing what I call inbreeding. And here I have a citation from two eminent professors we have here, Partha and Simon, and it goes as follows. If the core problems of the environment are in great measure ecological, their causes are largely anthropogenic. This means that appropriate solutions need to involve partnerships. So my little contribution to this partnership is to study particularly public goods games and, as I said before, common pool resource games, and I try to introduce some ecological dynamics. I'm also interested in norms, and I will come back to this. In particular, with Simon and other colleagues, we looked at the effect of ostracism in the evolution of cooperation. So now I have a video, also in the spirit of trying to keep attention and keep you engaged. I'm not sure the audio will work. Let me see. First of all, there should be internet. The idea is to motivate experimental work. If the audio doesn't work, I can... Yeah, you don't hear. So I will have to explain it first. This is an experiment that was run with capuchin monkeys, so not my type of experiment, but I will come back because this is making a point about fairness in animals, and much work has been done recently on fairness and social preferences in humans, and they're quite related. So in this experiment, there are two monkeys. It's a capuchin monkey version of the Ultimatum game, in a way, although with its differences. They want to elicit sort of a response to injustice. So the capuchin monkey on the left is given a reward for a task. The task was to exchange a rock for the reward. He's given a reward which is, in economic jargon, Pareto dominated from the other one, in the sense that it's not as good. It's still good, but it's not grapes, which is the favorite one. So because the two monkeys can observe what happens, and they are doing exactly the same task, so obviously they have some expectation about what is just. Let me just run it for you. Hopefully it will be clear.
That's the task, and we give her a piece of cucumber and she eats it. The other one needs to give a rock to us, and that's what she does.
So the monitoring. Now she gets cucumber, which she likes not as much. Boom! Again. She's given the cucumber. Okay. So unfortunately, I don't do such fun experiments myself. What I do is experiment with students with computer terminals, but we can try and elicit responses also from students. So this was run by Ernst Fehr. Simon referred to him before. He has been doing a lot of these games about retaliation, punishment, and fairness. So without going too much in the detail, the idea is, so in the Ultimatum game, for those that are not familiar with it, we have a decision tree here. As you see, if you can read, the payoffs on the left are always the same. So there is a proponent and a respondent. In order for the sum of money to be transferred to both, they have to reach some agreement. In case the respondent doesn't accept the offer, as you see from the branch leading to 0,0 on the left side, that means that both do not get anything out of it. So they, ideally, in terms of efficiency, they want to make a proposal which is accepted. They had different treatments. So what really matters here is the alternative. So it's a little bit like what we saw before, in the sense that there was a justice decision. So the respondent in the first treatment, the proposer in the first treatment could propose the split between either A2, so A2 means that 8 goes to the proponent, 2 to the respondent. And the alternative, so the choice was between X and Y branches, the alternative was 50-50 split. So let's say that it's $10 or 10 euros, then if the respondent accepted, both would get 5. In the different treatments, you have more unfair options. So the left-hand side branch is still the same, but, for instance, this is a 2-8 game. If the respondent accepts here, it will be a 2-8 split. And again, in case of rejection, it's 0-0. So here, more goes on one side, and you have this kind of injustice. And then you have the reverse, so you have 8-2 in the alternative treatment. And finally, so this is basically there is no choice by the proponent. Either way, the proponent gets 80% of the money, of the pot. And finally, the last treatment, the 10-0 game, actually is even worse. So if the proponent goes this way, then again, he would get 80% in case of acceptance. If it goes this way, he actually would get 100%. So basically, there's nothing in, in case of the right-hand branch, everything goes to the proponent. So what did the respondent do? Well, what they see, so in the first one, in the first treatment, the 50-50, you have a rejection rate of approximately 50%. But of course, what the alternative is matters, right? So the respondents realized this is the extreme case where the alternative is even worse, and here only 10%, I think one group out of 10 rejected. So intentions, these two experiments, in my mind, prove the point that intentions do matter, and when evaluating policy, we should take these distributional issues very seriously. And in particular, what I'm thinking in this lecture is whether we can find a sort of a burden sharing agreement that helps protecting the environmental commons. Okay, now moving towards climate change in terms of interpretation of these type of dynamics, we know there's wide participation to the Kyoto Protocol. This is the latest map for the new period, but you see that most countries have joined in. But however, if you then look at actually what it means in terms of commitments, so here only the dark black countries have commitments that mean restricting below the baseline level, which I think is 1990 emission, it's quite few. This is another green picture. Basically, if you look at just emissions, even if we've had almost 20 conferences of the parties, they've been going up. In fact, even the rate of increase has been going up. So it's not looking very well, despite all this communications and effort to cooperate internationally. So now I tried to frame these issues with the aid of game theory and these prisoner's dilemma and public goods dilemmas. We have already seen them before, so in the interest of time, I can be quite quick at these definitions. We talked about non-excludability and non-rivalry. And these are captured, these features are captured by very simple games, at least some of them. We also talked about the n-person prisoner's dilemma, or public goods game, which is a sort of a version with n players. So just to get a grasp of why this game captures some of these issues, defecting is the dominant strategy. So these are the payoffs for player one, so the one choosing here between cooperate and defect, given that player two has made one choice. So if you see, if player two cooperates, then the dominant strategy here is to defect because you don't pay the cost. C is the cost, B is the benefit of cooperation. Likewise, should player two defect, I'm still better off also defecting. Otherwise, I will just pay the cost and be the sucker. So, of course, we can think of it in this more general n-person version with the return, I is the number of cooperators. Again, defecting is a dominant strategy because cooperating has this additional cost. And we can draw a parallel between what this means in the game in terms of collective action with what we're facing with climate change. Unfortunately, no country can single-handedly go about solving it, so there's no unilateral action that can fix it. And this diffusion over time and space means that the country that reduces emission bears the cost, but only gains a small fraction insofar as there's a global dilemma. And in particular, with the two experiments I will be talking about, I will introduce threshold effects. I will be more specific about it, and we want to see whether this can aid with catalyzing cooperation. To just have another graphic representation of what we just saw, so this is a typical graph in international environmental agreements model where you have, this is the payoff I get, so player I, given that n minus 1 countries at most, so depending on the number of other countries taking action or not. And as you see, the red line is the payoff when a country I pollutes, and then if I decides to, say, fully abate and be more proactive, then it gets this lower payoff. And then this gives rise to the typical pessimistic prediction of a very small number of countries that can go about it and provide a stable coalition, which is captured by this number, which is the greatest integer greater than the cost over the benefits. So the prediction, which unfortunately so far has materialized, is that there will be small coalitions and they will do very little with compared to the status quo. Now, can we get out of this prisoner's dilemma trap? This is one way to represent the BAS model, which is about diffusion. And there's been much sort of a resurgence on the literature on diffusion, I think fueled by the book by Gladwell on tipping points, so not just scientific interest, but also more popular science, and about diffusion of innovations. But this is actually, more than just popular science. There is quite a wide literature on the fact that mutually reinforcing choices lead to accelerating diffusion in many domains. So can this also apply to environmental problems? And this, briefly, I have a couple of examples from a recent paper by Jeff Hill and Kuhn Reuter, where they motivate the importance of tipping in climate negotiations with examples that have taken places before. So one is the adoption of unleaded gasoline. In the case of a unilateral adoption by one big player, the US, this sort of fueled a response, a reaction by other countries, since all of a sudden a European exporter, if they wanted to continue to export to the US, they had to adapt. And so this quickly transitioned to this new equilibrium, if we want to reason in game theoretic terms. And this is what we mean by coordination games. So the introduction of this tipping point idea means that effectively you have two equilibria, still the defection one, where no much action is taken, and the Pareto superior one, where players get a higher payoff. The same applied with the Montreal Protocol. Again, this was a technological improvement by DuPont, which made phasing out CFCs actually feasible and economically reasonable. And due to strategic complementaries, other countries followed suit very quickly. And there's more examples in the literature on, for instance, with farming techniques, and even in a network-specific environment for microfinance programs in South Asia. Now, let's talk about the games that I've run in the lab and that I want to refer to today. So we have 6 players. They're playing a public goods game with a threshold and also some dynamics. So they play 10 rounds. It's not repeated public goods game, but it's actually, you have to look at the entire dynamics, and only at the last round you decide whether, depending on the investments by the group, it will be apparent whether they have reached the threshold, whether they have exceeded the threshold, which you can think of in terms of dangerous simulated climate change or not. So they're given an endowment, and in each round they get to choose how much they want to contribute to the public good. The idea being that the group needs to invest at least 120 euros in order to avoid some catastrophic outcome, which is what we have here. And importantly, differently from the standard public goods game, here you have this coordination game situation where you have also the Pareto optimal outcomes, which are supportable. So in a way, this game is easier than a standard prisoner's dilemma. We did 2 experiments. In the first one, we wanted to introduce some ideas of asymmetries, so poor and rich countries in the lab. And also, we allowed players to make pledges, similar to what happens in the negotiations. And then we went back to this game, but we introduced risk and ambiguity over the location of the threshold, which is something that seems to be the case also for the climate change problem, where we don't know exactly, is it 2 degrees, is it 3 degrees? And even if we agree on a temperature that we deem safe, there's no scientific understanding or sort of one unique way of thinking about what commitment in terms of economic commitment that is, in terms, say, of GDP reduction, if any. Okay, so the first one, as I said, we had rich and poor players, and we had this threshold, and they knew that in case of group failure to reach the threshold, they would lose half of their endowment. They will lose their endowment with 50% probability. So the classical prisoner's dilemma equilibrium is that nobody contributes at all, and then you have this 2 contribution by each player per round, so that's 20 euros over the entire 10 periods, which would deliver the 120 euro investment which is required. This is a graphical representation of it compared to the picture we saw before for international environmental agreements. So this is the payoff when I contribute, and this is the payoff when I always defect. And you see that this is why there is the Pareto superior equilibrium. If all other players contribute, I'm better off by contributing as well. Otherwise, it always pays to defect. Can they coordinate on this target in this simplified setup where the threshold is certain? So this is results. So we have a baseline treatment where we have 50% success in avoiding the threshold. Here they didn't have the ability to make these pledges. If we introduce the pledges, that goes up to 80%, so 8 groups out of 10. However, if we start again without the pledges and we just look at inequality, so some are poor, some are rich, so you have some kind of self-serving biases potential given that the two different groups have different stakes in the game. You see only 2 of the 10 groups succeeded. But however, if you reintroduce inequality, the pledges, that went up to 60%. So these differences are significant. And so we see that coordination, especially in absence of communication, this is reminiscent of Ostrom's work, can fail very easily. And unfortunately, the inequality doesn't help with this. This is another way to look at it. So this is on the left-hand side, we have successful groups that managed to avoid the threshold. Basically, a perfect redistribution took place where in the end, poor and rich had the same income. However, here we have this unfair division in the failing groups. Not only, so this is the average investment in these groups, which is 93. So it's quite high compared to 0. So they didn't really play the Nash equilibrium, but it's still quite below 120. And you see this unequal split, about 60% of the poor were contributed to the threshold and 40% by the rich, different shares. So to see how they use these pledges, these mechanisms for communication, we can look at this 45-degree line and compare contributions. So this is contributions in the rounds 4 to 10 versus the pledges. And in successful groups, so the 2 charts on the left-hand side, you see they cluster around the 45 bisectors, which means pledges were quite close to what they eventually contributed. While you have a high dispersion in failing groups, so there was some kind of strategic utilization of pledges which were generally above actual contributions. So just to summarize what we get out of this, communication is important. There was disagreement about fairness. We saw this also in questionnaire analysis at the end of the treatments, and hence this idea of self-serving bias. Of course, there's many things that are not captured. You have to make some sacrifices when going to the lab. And in particular, we wanted to play around with uncertainty on the location of the threshold. So we went back and did just that, building on both theoretical and experimental literature. And again, we had a similar setup, 10 groups of 6 players with the same endowment. In the certainty and risk treatments, they had an expected value of the threshold, which was 120. Well, certainty they knew, so the certainty case is the same as what we saw in the previous games. In risk, there was this uniform distribution, so all potential thresholds were equally likely. And on average, so the expected value again was 120. And then we had one treatment with ambiguity, so there was some task, uncorrelated task, that generated a distribution which was unpredictable. The threshold would be drawn at the end, so they had to play just based on this information. And I don't know if you can read. Yeah, should be okay. So again, you have the 2 instances in which you can make pledges or proposals. So more or less, these are similar across treatments. They cluster around the 120, the threshold. But then when you look at the contributions, well, in certainty they were spot on. With risk, they were about 100 out of 120, and with ambiguity, they further went down to 83. And interestingly, also the spread varies quite a bit. So in certainty, they're quite close to the threshold at the mean and max. But the more, well, as we go to the uniform distribution, you see they range from about 60 to 122, and then they drop to 26, the minimum in case of ambiguity. Given some hypothetical thresholds, remember this is the one that is the expected one in certainty and risk. We can also look at the success of different groups, and in certainty and risk, the success is always higher than in ambiguity. In fact, in ambiguity from 120 and above, they never would have made the threshold. We can also look at the dynamics over time in these 10 rounds, and you see so that the ambiguity and the risk, so this is the ambiguity, this is the risk treatment, and then the certainty one. So as often is the case in these public goods games, there is some kind of decrease towards the end in contributions. They sort of gave up the task. This did not happen under certain threshold. So in a way, the message is that it's a lot easier with a certain threshold, but again, in the real climate dilemma problem, we don't have the luxury of certainty. So just to summarize what we saw, uncertainty does decrease contributions. The proposals are used as a signaling device, so pledges still help, but it's very important whether early action takes place. So if players got off to a good start, generally they were much more likely to be successful. And again, we saw this burden sharing issue of how to split the pie, and it is quite important in the first experiment to counter the inequality. So if we want to extrapolate, always a difficult thing to do with lab experiments, but there is, in terms of incentives, it seems apparent, and this obviously is evident also from the kind of negotiations that have been going on between the North and the South, that there must be a crucial aspect is a willingness by the rich to concede this advantage, which is often perceived as unfair or due to past emissions. However, the negotiations are not framed in a way that makes this task easy, given that they revolve around future emissions. So business as usual emission growth paths are unobservable, so we have this comparability problem that is often referred to. So maybe a better way it would be to try to bring these equity concerns out into the open in negotiations. Okay, if there are no questions about the experiments, I will just move to some simple models that Simon and Maya Schluter and I have been playing around since when I was in Princeton. And so here it's a different kind of game, but as we saw in Simon's presentation, is quite related to the public goods game. So what we have in mind when framing these games, we have a common pool resource, and individuals decide on extraction of the resource. We have seen a lot from Marino and the previous presentation, so I won't have to go much in Ardeen's predictions. Of course, these predictions, as the work of Ostrom and others have shown, rely on certain conditions which are not necessarily always verified, such as open access and the absence of norms, absence of communication, etc. So we know that there is a lot of empirical evidence of self-organization with norms, and two important drivers of these have been shown to be the system at hand and the type of community. So using this framework, and to introduce a bit of notation on this model, we have n users. We think of a norm of ostracism. So here we have the effort of the cooperator, the effort of the de facto. I will come back to this, and this ostracism function. There's a productivity which depends on the group extraction and the resource. So this is all very standard. We just saw it. Then there's a carrying capacity and the dynamics of the resource. So again, we have some experimental and also field evidence, including that of Maya in Uzbekistan, that shows that there's a lot of this coexistence of norm and resource patterns. And we try to capture that by introducing dynamics. And of course, we build on the seminal work of Dasgupta and Hill, their book from '79. And also we start from the literature on the evolution of cooperation in common pool research. So Sethi and Somanathan in '96 had this AER paper from which we borrow some of the approaches, and the idea is that of imitation over time of successful strategies, and that there's been some understanding of what an acceptable level of extraction is. And then we will try to look into what happens when we introduce uncertainty, both in terms of research and institutional uncertainty. So we're sort of trying to integrate different strands of the literature and integrating resource dynamics with social dynamics in the form of replicator equations. So a very simple toy model of a coupled social ecological system. So again, I don't think I have to spend time on this. You have symmetric sort of mean field approximation. You have a reservoir. You can think of it as an underground water reservoir or some other resource with an influx, with a constant inflow C. And in the absence of the human intervention, so if you just look at the first part, this is the dynamics of the resource, which can be depicted as follows. Of course, once you introduce the social aspect, things change. So two types of strategies, cooperating and defecting. They just differ in the extraction level, that ED is the effort of the defector, EC is that of a cooperator. You have a payoff function, a materialistic payoff, which is given by the effort exercised, given the net average product, net of the opportunity cost of labor. So very standard. I guess the take home from this picture here is that you have sort of open access level at the right-hand side, and then you have the efficient level, which would mean restricting extraction to what is socially optimal, going back to Partha's lecture, and the Nash equilibrium is somewhere in the middle, quite close to the open access in this setting. So we depart from previous literature by looking at this ostracism norm. So now the utility for the cooperator is simply the materialistic payoff pi c, but for a defector you have the payoff from production, which is higher than that of a cooperator, but that and this is sort of not too distant from what we saw before with Partha. We have some kind of inequity aspect. So there's an intensity of defection which is captured by the difference in payoff between the defector and the cooperator, normalized by the defector's payoff. So the idea is that these violations of the norm are observed, and then this ostracism function, which is a function itself of the frequency of cooperators Fc, models how stringent the response is. And in particular, so this is that omega function. The idea is that there is some inflection below a certain frequency of cooperators. Obviously, they cannot ostracize because there's simply too few cooperators and too many defectors. However, as you have an increasing percentage of them, they become more and more effective in ostracizing. And we can look at the dynamics so to capture this idea of coupled social ecological systems. When you have more cooperators, you have more resource, which means that the defectors actually gain more, so you have an increased incentive to defect, which increases the utility of the defector. However, with more cooperators, due to this ostracism function, you also have more disapproval, and they're more effective in reducing the utility of the defector. And in terms of which strategy to choose, so we're not looking at the equilibrium concept of static game theory. We have this dynamics, and again you have this replicator dynamics idea of imitation of successful strategies, where you tend to switch to the strategy with the higher payoff. This picture we have seen before with Simon. It just tells us that contrary to models where there's no ostracism, by introducing this dynamics, we have also a coexistence equilibrium, which is stable. Mu here is the intensity of defection, so a mu equals to 2 means that defectors take out twice as much as the efficient level, which is the cooperator's extraction level. We only have 2 strategies at a time, but we look at what happens for different levels of defecting strategies. And the cooperators are always at 1 compared to the efficient level. And here on the x-axis we have the frequency of cooperators. So If we have enough initial cooperators, we can transition either to the cooperative equilibrium, so full cooperation, or for higher mu, so for higher intensity of defection, we would stop here at this polymorphic equilibrium where they coexist. And of course, we still have, and you see the basin of attraction of the defector equilibrium is larger. Now, there's been some extensions of this work. This one by Chung and others using network analysis. So, well, they introduced some topology in terms of regular networks of different degree. And in the limit of the complete network, of course, they recover our results, which would be the ones with these black lines here, black curves. And here you see these other different curves. They are related to different degrees. So the regular network with different connectedness. And their finding is that, again, in the limit case of well-mixed population, we have the same result as before, but this is destabilized in loosely connected networks with a small degree. We wanted to see the effect of variability in the resource. So here we have some variance, some variation on this C, which before was constant. That's the inflow. And with these simulations, we show that actually with a higher variability in this model setup, cooperators tend to fare better, and that comes from the concavity of the resource function. So in a way, you can think of it as an insurance argument. While both cooperators and defectors with variability do worse, cooperators can still bank on this ostracism, while the defectors face ostracism by the cooperators, and ultimately they're made worse off. Another extension we did was to look at these bifurcation diagrams in a setting of generalized modeling, and we wanted to see this time what would happen with increasing resource. So as we move to the right, the resource is increased, and we have evidence of these regime shifts, right? So you start here at 100% cooperation, and then as C increases, you get to a point where you end up on this trajectory, which leads to 0% cooperation, full defection. The one on the right-hand side is just a linearized version of the same for robustness purposes. So what we see is that initially increasing resource level leads to a greater increase in defectors, so the benefits to defection increase, and that, of course, has impacts on the resource, which eventually becomes overexploited. So let me just summarize the findings on these two or three graphs that we've seen for the social ecological system. We have that cooperation can promote sustainable resource use, so we do find under certain parameterizations full cooperation. Of course, this only takes place when the violation of the norm isn't too large, and there's enough members of the community that are engaging in this ostracism mechanism. For larger violations, so for higher mu, either coexistence or widespread defection, so the full defection equilibrium take place, and that depends on the threshold disinflection point in the ostracism function. And then we saw with the extensions that I just showed that there can be sharp transitions between the non-cooperative and cooperative outcomes depending on the stringency of the norm, and that also variation in this C, the inflow, can have detrimental consequences and cause a regime shift. So let me just try to wrap up the entire presentation and see whether we can find some persistent patterns. While different games, and some in the lab, public goods games with respect to common pool resource games, as we saw, there's quite a bit of similarity in the two, and here in both we have explored the role of thresholds in catalyzing or disrupting cooperation. And I think one takeaway message I would like to convey is that, of course, the scaling part is important. We have to be careful when aggregating impacts at the national and global scale, so the issue of scalability, and that norms can, well, either hinder or promote cooperation. But for instance, in the case of the lab experiments, we had these self-serving biases which were detrimental for cooperation. So unpacking this black box does allow you to have different insights on the picture, and maybe, you know, also to introduce the potential bargaining opportunities that should be discussed at the negotiation table. Of course, when we think about global dilemmas such as climate change, that means we need some kind of transformative change, both in technology and in behavior, to avoid the catastrophic potential consequences. And for these, you know, it seems that both the efficiency consideration and distribution do matter. We don't have really a price on carbon yet, so that I guess is still work in progress. And as I argued in the beginning, I think multidisciplinary collaborations that tackle this type of complexities are necessary to approach these difficult and complex social ecological systems, which do feature both social and scientific uncertainty. And I think this was my last slide. Yeah, I have just some references for you. Thank you.
Thank you so much, Alessandro. Very interesting indeed. And Partha?